Hi, my project is 3D printing personalized knee implants for meniscus tears. My mom has had arthritis near her knee, and last year that caused a meniscus tear and she had to have surgery to remove it. I found that current treatments, such as this surgery, have been proven to actually worsen arthritis. This fueled my curiosity, so I joined a biomechanics lab to try and create a new solution. The meniscus is the blue area here, and its main function is to act as a protective lining and shock absorber. The big issue today is that the menisci are prone to tearing, with over 1 million Americans having meniscus tears, making it the most common knee injury, with an annual burden of $2.9 billion. Cartilage cannot naturally heal, and that's what makes treatment so difficult right now. So in the context of a professional athlete, you need a complete recovery, but commercially available implants don't support new tissue regeneration because they don't mimic native tissue and are not personalized to each patient's specific tear. So my research question aims to develop a truly representative meniscus implant, and I answered this with 4 big steps. First, personalizing, then optimizing, 3D printing, and finally testing it to make sure that it can truly support torn tissue regeneration. So my first mission was to personalize my implants, and I did this by modeling them after real patients' meniscus tears. I used MRI images that are publicly available on NYU's fast MRI datasets. I then reconstructed the shape of the patient's torn meniscus and got a 3D model of what my implant needed to repair. I then used a software called Entopology to lattice the shape. Latticing essentially creates a 3D matrix with similar fibers and pores as real meniscus tissue. I then optimized the structure using finite element analysis, which is a computer simulation that allows me to put different loads and pressures on my implant to see how it reacts and if it would tear. This force was 20, 60, and 80 newtons, or the equivalent to a blunt force injury in sports and common knee pressures. My implant was then optimized by reinforcing areas most prone to tears. Once my latticing and design was complete, I 3D printed the scaffold, and the image on the middle shows the result. The material I used was polycaprolactin, or PCL, which is commonly used as a biocompatible polymer for bioprinting and has promising orthopedic applications. However, the big issue I wanted to address next is that current implants have 45% empty and negative space, and this is what makes cellular integration and matching the structural strength of the meniscus such a challenge right now. Because my scaffold's lattices are so porous, I integrated a hydrogel made out of composite gelatin and chondroitin sulfate. The reason I chose these materials is because the meniscus is 72% water, 22% collagens, and 0.8% structural sugars, so my hydrogel matches the physiological composition of cartilage tissue. My final product is an implant made out of a PCL scaffold combined with gelatin and chondroitin sulfate hydrogel. Once I had created my final test, I had to characterize it, and to this extent, I studied the structure as well as biocompatibility. I directly compared my implant to pig meniscus tissue, which is representative to what real human tissue acts like, so it was my positive control. First, I used scanning electron microscopy and micro-CT to study the surface. The reason why this is so important is because stem cells grow in pores in tissue, and they have a pore size that best facilitates cell survival. As you can see in this image, my implant had 3 distinct regions that directly mimic the 3 regions of meniscus tissue, and this high specificity is only possible because of my unique 3D printing process. I found that the average pore size throughout was statistically similar in my implant to pig tissue, with an average of 215 micrometers. Afterwards, I conducted a rheological frequency sweep as well as unconfined compression, and these 2 tests show the strength of my implant. That's important because the meniscus has to absorb all the shocks in the knee, and these assays show that my implant behaves similar to pig tissue when put under stresses that replicate the real condition in the knee. Once I had structurally tested it, my next mission was to culture ligament-derived stem cells on my implant to see if it could support cell growth. I found that my implant supported 50 times more cell proliferation, but my biggest question was if those stem cells were differentiating into fully functional chondrocytes, the cells that build up cartilage. To test if my implants actually guided those stem cells to differentiate into chondrocytes, I used 3 specific cell stains which detect key phenotypes of cartilage cells. I found that my novel design supported 97% more differentiation in just 7 days. I was able to conclude that my new design was able to mimic real tissue while making sure that cells proliferated and differentiated. The way my treatment is able to augment knee injury recovery is that it's patient-specific. It's rapidly prototyped, meaning that physicians can have a design for an implant within minutes of diagnosing a tear. My novel implant materials also cost 200 times less than current implants, meaning that more patients can access this new treatment. Thank you so much for your time.